series. So we want to talk about what's called power series. And before we do that, let's talk about the geometric series. So the geometric series can be rewritten with an index starting at 0 instead of 1. So we've always, for the most part, we've been starting their index, the index being, this value I or j. That's called the index. And so from here, the vast majority of the time so far, we started that value at 1 because that represented which term of the, then the I value represented which term of the sequence we had. So when I was 3, that was the third term of the sequence. And when I is 5, that's the fifth term of the sequence. And so that's possible when you let the first term of the sequence be I equals 1. But you don't have to have that, right? So you can start I kind of at any value, and another common value to start at is 0. Then it starts at 0, but then the first term of the sequence is for I equals 0. And the second term of the sequence is when I equals 1. So you don't have that nice match, but it's still a completely legitimate way to write a sequence or a series. So we're going to rewrite this series 0. But before we do that, I want you to write out what this means, right? So we've been working really hard at what are the meanings of these expressions that, to some may look scary, but they don't look scary to us. Okay, so because we know what they mean. And so I want you to, when you see this, you think what, right? You see something like this and you immediately think what? Write it out, okay? Write it out, what you think, what this means when you see that. And we said this is foundational, right? We don't want to do all this complicated analysis if we can't really look at that and say, oh, I know exactly what that is. It means this. And so then write it out. Okay, do I have a volunteer to tell me what I should write here? When you see this, you think what?
So we'll start with A
A
plus AR squared,
okay,
and plus AR to the third, and so on.
and so on. What about the rest of you? Do you agree with what she said?
Yep.
Good. So yeah, so you let I equals 1, and you find what this is. It's A. And then you let I equals 2, and you find what this is. It's AR. And then you let I equals 3, and you find what this is. It's AR squared, etc. And then this says sum up all those things, right? Sum up all those things. First when I equals 1, then when I equals 2, then when I equals 3, and so on. And this means keep going forever, right? Never stop. Okay, so what we want to do then is we want to write this we want to get these same exact terms, but we want to start with I equals 0. So what should the formula be? Now looking, we want to get the exact same terms. What should the formula be so that when I start at I equals 0, instead of I equals 1, and so I equals 0, then I equals 1, then I equals 2, I get this exact same series. What should the formula be?
AR to the I.
Okay, someone wants AR to the I. Agree? Let's try. When I equals 0, what do you get? Just A. When I equals 1, you get AR. There it is. When I equals 2, you get AR squared. Okay, so this is what's called shifting the index. We just shifted the index, but it didn't change the series, right? So this looks a little bit different than this, but it's the same series, right? It's the same sum. Okay, so notice what happened. If you reduce the index by 1, what do you have to do in the formula?
Add 1.
Increase by 1, right? So if you move the index back by 1, then to get the same terms, it should make sense. You're going to have to add 1, right? So that to compensate for moving back all the indices by 1, then you're going to have to move these forward by 1 or add 1 to get the same terms. Okay, does that make sense? So here's a new way to describe a geometric series. Rather than I equals 1, AR to the I minus 1, you'll often see geometric series starting at 0 and then simply being AR to the I. But then we see we get the exact same, it's the exact same series. It's the same terms. So this is a little cleaner way to do it. The disadvantage now is that I doesn't stand for the term number anymore, right? I equals 5 is not the 5th term, but rather, what is it? The 4th term or the 6th term? 0 is the first. So that's the 6th term, right? So I equals 5 now means the 6th term instead of the 5th term. Okay, questions on that? So you'll often see these series starting at 0 instead of at 1, and it makes perfect sense. So you just start at 0 now. Your first term will have I equals 0 rather than 1. Okay, so now we're ready to talk about a power series. A power series is a series of the form. So notice I'm starting at I equals 0. And so what you have is a real coefficient, which could change according to I. So this is the ith coefficient, times x to a power I. Okay, so again, see this, think what? Write it out. Practice. See this, think what? Write it out.
It'd be ci plus cix plus cix squared plus cix cubed.
Okay, but ci, what was ci? This is the index, right? So this I is the same I as this one is the same I as this one.
So the first one would be
So-
c sub 0 x to the 0.
So how about the gentleman that spoke up before? Do you want to try again?
Sure.
Yeah.
So it'd be c to 0 plus c1 times x plus
There you go.
c2 x squared,
Right.
and so forth.
Right. Good. So now the coefficients can change according to I, so that we use the subscript. Right. So we've got these coefficients, these varying coefficients, and then the varying powers of x. So what's different about this than the series that we've seen so far?
The star coefficient changes as the index changes.
Well, we had varying terms, right? So this is just, we had varying terms. That's we've seen that before.
We have a variable.
Yeah, we've got this x in there, right? We've never had a variable before. Before, we always just got actual numbers, right? Every term ended up being a value if you simplified it. So it was one number plus another number plus another number. Now we have a variable x as part of our terms. And then, so what do you notice about this x to the first, x squared, x cubed? It's all whole number powers of x. Does that remind you of anything from your algebra and calculus past?
Polynomial.
Polynomial, right? So good. So this looks like a polynomial, right? Real coefficients times whole powers of x. So what a power series, but what's the difference between this and a polynomial then? So there's one difference then. So yes, this is exactly the form of a polynomial, but what's the main difference to the polynomials you've seen in the past?
It's not continuous.
It will be continuous if x is a real number. It'll be continuous.
It has an infinite number of terms.
Good, right? So it goes on forever, right? So this is just like a polynomial, but the one difference is you'll just keep adding terms forever. So it has an infinite number of terms. So we want to think of these power series as, so we got a real valued coefficients depending on I. X is an independent variable. And so we want to think of these as, these power series, like a polynomial, but with an unlimited number of terms. So think of this as like f of x as some polynomial function. So this is what defines a power series. It's like a polynomial with an infinite number of terms. Okay, but notice, so what will happen? The powers on x will just keep getting bigger and bigger and bigger and bigger. So what's the question here? So we have there's a question that begs to be asked here, right? What's the question that begs to be asked about a power series? I mean, isn't this thing just going to blow up, right? If you have a bigger and bigger power of x.
Can it ever converge?
Right. It's about convergence. And so specifically, we want to know, this is the big question about power series, for what values of x will the series converge? And then subsequently, the other values, the series will diverge. So this is the big important question about power series, right? So x can vary. So since x can vary, so we're going to look for certain values of x for which the series will then converge, sum up to a finite number, right? Converge means that all those will sum up to a finite number. And then other values of x, this thing will blow up, right? It'll just get huge. Okay, so again, review. What's a power series like? It's like a polynomial with an infinite number of terms. That begs the question, and our whole focus then for these is, for what values of x will the series converge, and thus when will it diverge as well? Okay, questions on that? So we're going to do examples, but any questions on the premise here? Okay, very good. So let's take this example here. So I got, notice x to the j over 3/4 j minus 1. So let's just see how that is a power series. So what did we say? C, so it would be, what is the jth coefficient then? So how would we rewrite this so it looks like this? What are our coefficients? C0, C1, C2, etc. Or what is the Ci in this power series?
It's the denominator.
Good. So the Ci would be 1 over 3/4 j minus 1. So that's our jth coefficient. And then we have times x to the j, so we see this as a power series. And what does that coefficient look like? This just looks like series we've seen before, right? These are the kinds of series that we analyzed, right? So some formula or function of j. But now it's times x to the j, that makes it a power series. All right, so we're going to use the ratio test is the main key to finding out when the series converges, because that tells us about the convergence of a series. So we're going to do the ratio test. So here we go. So remember, we're going to do the limit of the j plus first term times the reciprocal of the jth term. And I changed from j to I for whatever reason. I didn't have to do that, but for whatever reason I changed, and that's fine. It's just a symbol. We could use j here or I. But the I plus first term would be x to the I plus 1, 3/4 I plus 1 minus 1, times the reciprocal. So you guys are familiar with that for power series. Okay, and so then we're going to look at our like things here. So so we can combine the x I plus 1 over x to the I. And what does that equal?
X.
That's 1x on the top, right? So this is I plus 1 x's multiplied together, and I x's multiplied together, so there's one more x in the top. And then what about the limit of 3/4 I minus 1 over 3/4 I plus the rest of this stuff? What about that limit?
Just equals 1, right?
1, right? Because it's the same power, right? This is a rational function, same power. So you take the ratio of the coefficients, leading coefficients, and you get 1, right? So that limits 1, and we're left with x. So all we're left with here in this limit is absolute value of x. All right, here's a better view of that. There we can see how that limit is going to go to 1 because of the ratio of 3/4 to 3/4. And we're just going to be left with square root of x, or sorry, absolute value of x. And when did the ratio test tell us that a series converged?
When the ratio that you come out with is less than 1.
The limit, right? So yeah, the limit of this sequence, right? When the limit of this sequence is less than 1, and we talked about how that relates to a geometric series, right? So when the limit of this thing is less than 1, so that will determine what values of x will make this converge if we take that limit and we set it less than 1. So what values of x is that? So we don't want the absolute value. We want to get an actual interval for x here.
Between -1 and 1.
Right. So thus the series converges for all x values between -1 and 1, because when x is between -1 and 1, our ratio test will give us a limit less than 1. What if x was -1? So if x was -1, what would the limit be?
It would be 1. And then
Right. If x was -1, the absolute value of -1 is 1. Same with x equals 1. And what in the ratio test, what did we say when the limit equals 1? What did we say?
No conclusion.
No conclusion. So at x equals -1 and x equals 1, the series might converge. It might not converge. And so what we can do then is just plug in x equals -1, and then we'll have like a series like we've done before. It won't be a power series anymore. If I plug in if I fix x to be -1, it won't be a power series anymore. It'll just be like all the series we've been doing for the last week. Same with x equals 1. So because these two values give a limit of 1 in the ratio test, we need to check those separately. We need to check those individually by plugging in -1 and plugging in 1 and analyzing those series with the toolbox that we have from before. Okay? So let's do x equals -1. So if you plug in x equals -1, you get this series. It's no longer a power series. X is gone. Now it's like the series we've been working on the last week or 2 weeks. And we have to figure out, is this going to converge or not? So we reach into our toolbox. And the first tool we apply is, what's the first tool we ask about? What's the first thing we always ask?
The divergence theorem.
Right. And the divergence theorem says, does this sequence go to 0? First of all, if the sequence does not go to 0, the series could never converge. So what about this sequence? Does the sequence converge to 0 as j goes to infinity?
Yeah, it does.
Sure, right? Because you got j to the first in the denominator. Alternating, that doesn't affect anything. You have j to the first in the denominator. So that's kind of like the harmonic sequence, right? Harmonic sequence, or a p sequence with j equals 1, kind of like it. So yes, so the sequence goes to 0, so now we can test it. So what does this converge or diverge?
I think it converges just because it's so similar to the alternating harmonic series.
Okay, so this thing, the non-alternating part, decreases to 0, but it alternates. Therefore,
I think it would converge absolutely, but not alternate.
so we're not talking about absolute versus conditional right now. We're just talking about does it converge or not. So the series, what does the alternating series test say? It says if your sequence goes to 0, and it alternates, right? If it decreases to 0 and alternates, boom, you're done. It converges.
I think it also mentions that the terms need to be positive, which is why I might be confused.
So after you 1, 2, after 2 and 3 and 4, then they're all positive to the end, right? So as soon as j gets up to like 2, then from 2 on, 2, 3, 4, 5, they're all positive, and that's all that matters, right? So as long as there's some starting at some point, as long as they're positive after that, then it's fine, and that's what happens here. So that requirement is generally met, even though the first couple terms are negative. That's not a problem. So converge or diverge?
Converge.
Converges by the alternating series test. This thing decreases to 0 as j increases, and it alternates. That's the alternating series test, so it converges. Okay, what about x equals 1? Here's for x equals 1. Here, so now when x equals 1, this 1 to the j just goes away. It just becomes 1, right? 1 to any power is just 1. So I'm going to plug in x equals 1. And then what about this? Converge or diverge?
I'm going to say diverge because the reason why is because it resembles a harmonic series in the sense that 3/4 j, if you like bring out the 3/4, like, you know, using algebra, then 3/4 j is smaller than j, and then subtracting 3/4 from that makes it even smaller, so the terms get bigger than it would in a harmonic series, so I think it would diverge.
So he's saying that the terms of 1 over 3/4 j minus 1 are all greater than the terms of 1 over j. Now, except for the first couple terms where these are negative, right? So when j equals 0, you get a negative. When j is 1, you get negative. When j is 2, and then they start becoming positive, then all these terms, because the denominator is less, the whole ratio will be greater. And so what do we know about, so we're using direct comparison here. We have a series that diverges, and then we have another series, the one we're looking at, all the terms are greater than the terms of the one that we know diverges. Conclusion?
Diverge.
Diverges by comparison to the harmonic series. Okay, so what happened? We used the ratio test to find the interval of convergence, but at the endpoints of the interval, we get L equals 1, which means no conclusion. So we plug those endpoints in, and now it's no longer a power series. It's just the series we've been working on before, and we analyze those separately. And what did we find? We found that this does indeed still converge when x is negative 1, but diverges when x equals 1. So thus the interval of convergence is negative 1 less than or equal to x less than 1. Okay, so we can graph that interval, and it will look like this. So on a number line, so here's the x values. So between negative 1 and 1, we have convergence of this power series. At negative 1, it does converge, but at all the way up to 1, it converges. But then when you actually get to 1, then it diverges, because it ends up being like the harmonic series. So one thing you can do here is we can imagine this kind of like a circle, this interval. We can imagine this like the circle which like holds all the values for which the interval converges. So like if you're inside the circle, it converges. If you're outside the circle, it diverges. And kind of in that vein, we have that, you have a radius, right? From the center of the interval out to the edge of the interval is called the radius of convergence. And this radius, the radius is a single value. The radius convergence is a single value, and it's like what? Half the distance of the interval. So in this case it's 1, because it's from 0 to 1 or 0 to -1 is the radius of the circle, and it's always half the interval, half the distance of the interval. So we'll talk about that this power series has a radius of convergence of 1, meaning that its interval of convergence has a width of 2. Does that make sense? Okay, so other questions on this problem? Really important problem. There's a lot going on here. We're pulling from a lot of things that we learned before to analyze this power series. So if I lost you in any particular aspect, please ask. Okay, good. So let's go on. There's another one here. Okay, here's another example. So how is it a power series? So we have x to a power. And then the rest of it would be like our coefficient. So this -1 to the k over 2k plus 1 factorial is like our coefficient. And so this power series, the 2k plus 1, what will we get for the exponents? Let's just write out the exponents. We're going to get, first we're going to get x to the 1. So we'll have c0. When k is 0, we'll have c0 x to the 1. And then when c is 1, we'll have x to the what? 3? And then when k is 2, we'll have x to the 5th. So in this particular power series, the subscript on the coefficient doesn't really match up with the power because this 2k plus 1, but it's still a power series. So what's happening here is it's a power series where actually the coefficients of x squared of all the even powers are 0. So it's kind of like we would need to rewrite this, I'll use capital C, as C0, these are capital C's now, C1 x to the first plus C2 x squared plus C3 x cubed plus ... And now all of these, all the even coefficients are 0 because that we don't have an x squared, an x to the 4th, and x to the 6th. Right? And so then the x to the first power, this is really the coefficient for the x to the first. So we could write a new coefficient. So that's equal to that. And then that's equal to that. So really, when k, say, for instance, when k equals 1, when k equals 1, we really get the coefficient for the x cubed term, and so that would be kind of like C3, even though it's when k equals 1. Okay, does that make sense? All right, so ratio test. Here we go. So ratio test. We're going to do the I plus first term times the reciprocal of the ith term. This is done this before. There's a lot to write here, but it's not too bad. We know that everywhere there's a k, you're going to put I plus 1, and then times the reciprocal of this. And you can just Speak out if you have a question anywhere here, if something isn't clear. All right, so then we're going to combine our like things. Remember when we said if you just have the plain alternating -1 term, that just goes away? You don't have to worry about that, because we'll just have a -1, but then absolute value will negate that. So then how many more x's do we have on the top than the bottom? So I think we got the next step here. There we go. Oh, no, we don't. So this is 2i plus what? 2i plus 2 plus 1. So this is 2i plus 3. And this is 2i plus 1. So how many more x's do we have in the top than the bottom? 2 more, right? So 2i plus 3 would be 2 more x's multiplied together than 2i plus 1. And then down here I got 2i plus 3 factorial over 2i plus 1 factorial. So we know that 2i plus 1 factorial is a factor of this, leaving what? So what is it? 2i plus 3 times 2i plus 2 times 2i plus 1, etc. That's where, and so this is where 2i plus 1 factorial starts. So we see that these expressions simplify to the first two factors, 2i plus 3 and 2i plus 2 in the denominator. Then all the rest of the factors cancel out with a 2i plus 1 in the numerator. So let's see that. So there's the x squared, there's the -1 in the alternating. And so that's what we said. So you're going to have the 2i plus 3 and the 2i plus 2 left when you simplify the factorials, and the x squared. And so what is the limit of this? So as I goes to infinity, as I gets really, really big, what is the limit of this?
0.
0, right? So this is just, this is a rational function. We got 4i squared in the denominator. So clearly this is just going to get, the denominator is going to get big. This will go to 0. And that would be true for any value of x. So you pick a value of x, square it, and that just becomes a constant. And then I gets much, much bigger than that, right? Whatever value of x you pick, I will get exceedingly greater because I is increasing without bound. So this will go to 0. And when did we say, for what does the limit have to do in order for the sequence series to converge?
The sequence also has to converge to 0.
No.
Or
This
to
sequence. The sequence of the ratio, right? The multipliers. What does
Less than 1.
less than 1, right? The ratio test says that. So we're asking then, for what values of x is this limit less than 1?
All values.
All values. Someone said all values. Does that make sense? So no matter what value of x you pick, this limit will be 0, which is less than 1. So pick a trillion. X equals a trillion. You're going to square it. You get a trillion squared. But when I gets infinitely big, it will be way, way bigger than a trillion squared. Doesn't matter how big of an x you pick, I will get much, much, much bigger than that because there's no bound to how big I gets. And so this limit is always 0, no matter what x is. And 0 is always less than 1. So what is our interval of convergence?
-infinity to infinity.
Yeah, x can be anything. This is saying that x can be anything, and this series will still converge. So all real numbers x.
Could we write that as, oh, never mind, you just did it. All real numbers.
Yeah, or this. You can write like this. So what's half of that? So the interval is from -infinity to infinity. So you could say it's kind of like centered at 0 maybe. So then from 0 to infinity is our radius. And that's still infinity, right? So the radius of convergence is infinitely wide, right? It's even half of the interval is still infinitely big. So the radius of convergence is infinite. The interval is all real numbers x from -infinity to infinity. So no matter what x you put in here, this series will converge.
So interval of convergence and like the radius, that's only for power series, correct?
Right, because power series, we're talking about what values of x make the power series converge.
Thank you.
Yeah, and power series are when we bring x into the picture. Other questions? Okay, one more example. This one. Let's do it. We're going to do the ratio test on this. So the ratio test says, we take the limit. So I actually haven't been writing that. I've been just starting with it's the absolute value of. So we're going to do the j plus first term. This should be j, not n. So -1 to the j plus 1, x to the j plus 1 over j plus 1, 2 to the j plus 1. Doing the ratio test here, right? What are we setting up? We're setting up the sequence of multipliers, the sequence that always is the multiplier to get us the next term, right? So it's kind of like we're seeing if this becomes a geometric, seeing if it becomes geometric, or for what values of x will it become geometric with an r less than 1. That's what we're saying. Okay, and then we're going to do the reciprocal, so we're going to have j times 2 to the j over -1 to the j, x to the j. So we're going to have one more -1 in the top, just for, we'll just write it. We know it won't make a difference in the end, but we can write it. How many more x's do we have in the top?
One.
It's one more x. How many, and then we have, how many more 2's do we have and where?
Extra 2 on the bottom.
One more 2 on the bottom. And then we have j over j plus 1. Okay, so what will this, as j gets big, what will this go to?
X over 2.
Absolute value of x over 2. As j gets big. That's 1. That limit's 1. And then the -1 in absolute value doesn't matter. You can just get rid of it since there's an absolute value around it. So then it'd be x over 2. So what we're saying, then absolute value of x over 2 has to be less than 1. And so that means x over 2 is less than 1, greater than -1. Or x is between 2 and -2. And then we have to check the endpoints. So then we check x equals 2 and x equals -2. Let's do x equals +2 first. When x equals +2, we get the series -1 to the j times 2 to the j over j 2 to the j. And so notice you have 2 to the j over 2 to the j, which is
1.
1. And so then I have negative 1 to the j over j. Converge or diverge, and why?
Converge because it actually is the alternating harmonic series.
Alternating harmonic series, we know that converges. X equals negative 2. We're going to get negative 1 to the j times negative 2 to the j all over j times 2 to the j. And so what's negative 2 to the j times negative 1 to the j would be, we could just combine those. We can combine all these. There's all to the jth power, so we can do 1 over j times negative 1 times negative 2 over positive 2 all to the j. And what is all that?
It's just 1 over j.
Yeah, so this is just 1, right? Because this negative 1 times negative 2 over 2, that's just 1. 1 to the j is just 1. So this whole thing is just 1. Converge or diverge?
Diverge.
This is the harmonic series that diverges. Okay, so what's our interval? So 2 is yes. X equals negative 2 is no. So our final conclusion is so positive 2 gave us a yes this time. Negative 2 gave us a no. So the interval of convergence is negative 2 less than x less than or equal to 2. And what's the radius of convergence?
2.
The radius is half the distance of the interval. Questions on this one?